Hello, welcome to Lesson 15, Chapter 5, Continuous Random Variables. So, up until now, we've been talking about discrete random variables. They can only take on a finite or countably infinite set of values, and they have a probability mass function that satisfies the conditions that the probability of any specific value for the variable x is greater than or equal to 0, and the sum of all the probabilities is equal to 1. Now, in the continuous case here, the random variable can take on an uncountably infinite set of values. For most of the problems we do in this course, we're going to be talking about a situation where the random variable can take on values over a connected interval on the real line. Some examples of continuous random variables: the life of a battery, so elapsed time, that's going to be continuous. The length of a piece of wood, the height of a human being, measurement, that's going to be continuous. Now, in a situation where you have a continuous random variable, the probability of any one specific value is actually assigned to be 0, which seems a little strange at first, but with an uncountably infinite large set of possibilities, the chances of any one of those values are assigned to be 0. It's essentially impossible, but which is a little bit counterintuitive because something has to happen. But in terms of assigning probability, um, the probability of any one value is assigned to be 0. Now, again, for the most part, we're going to be dealing with intervals of real numbers here, but you can extend this out to a definition for any measurable set. If you've taken analysis, you may have come across that. But again, for the most part here, even though the definition extends out to more messier situations, we're going to stick to intervals in this course. But for any measurable set B, the probability that x belongs to the set B is the integral over B of um, f of x dx. But again, for this particular course, we're going to stick to the more familiar situation where we're working on an interval of numbers. And so we're doing a definite integral from a to b of f of x dx. And that represents the probability that x is between a and b. So it makes sense here that the probability of any one value would be 0 because we would have essentially just a line here, and we'd have an area of 0. We would need to have um, uh, excuse me, we'd need to have a positive here width here to go with this height in order to get a positive area out. So the probability of any one value is assigned to be 0. Now, this function f is called the probability density function, and it's going to have some familiar properties here. It has to be greater than or equal to 0. So the function is defined from the real numbers to the positive reals. And the integral from minus infinity to infinity of f of x has to be 1 in the same way that the sum of all the probabilities in the discrete case had to be 1. Here, the sum is done by integration. So the integral here, this area, has to be equal to 100%. The probability that x is greater than or equal to a is the same as probability greater than a. Remember, any one value has probability 0. That probability is the integral from a to infinity of f of x dx. That would be everything to the right of a. Probability that x is greater than a. And if we used a less than or equal to or less than, again, both the same, we'd be integrating from minus infinity to b of f of x dx, which would just be the antiderivative of a little f. Let's call that capital F of b. That's the area to the left of b. That would give you the probability that x is lower than b. If you want the area between, then you do the traditional definite integral from a to b, f of x dx. And so this last situation, the probability that x is less than b, less than or equal to b, that is the cumulative distribution function. That is the CDF of x. It's current probability and all the previous ones accumulated. So the capital F function is taking on that role, or at least can take on that role of being the CDF. And from fundamental theorem of calculus 2, the derivative, antiderivative undo each other. So the derivative of capital F is the derivative of the integral, f of x dx, and those cancel out to just f of b. So f prime, the derivative of the CDF gives us the density function f. All right, let's take a look at an example here. This is a classic example. We're given a density here, probability density function, PDF, for a continuous random variable, defined in terms of some constant k. We have to find that constant that makes this satisfy the conditions. We need the expression to be greater than or equal to 0. And we need the integral minus infinity to infinity over the whole real line to be 1 whole 100%. Now, in this case here, where the function is 0, except for the x values 1 to 3, we don't have to do an improper integration. We can just integrate from 1 to 3. We only have to work with the non-zero portion. So we have to show that this definite integral from 1 to 3 of f of x dx is going to be equal to 1. We have to figure out the k value that's going to work here. So we're going to be able to factor out k, it's a constant, and then do a power rule to integrate 1 over x squared. So that's going to come up as x to the minus 2, and then we're going to do a power rule on integrals there. We're going to add 1 to the power, divide by the new power. So it's going to be x to the minus 1 over negative 1 from 1 to 3. K times that has to equal 1. X to the negative 1 is the same as 1 over x. So it's negative 1 over x from 3 to 1. And then we do the fundamental theorem, f of b minus f of a. And so we get k times negative a third minus negative 1 over 1. So that's negative a third plus 3/3 or 2/3. K times 2/3 is 1, so k must be 3 over 2. So 3 over 2 is the constant we need here so that this function f satisfies the conditions of being a probability density function. And then part B was to calculate the probability that x is greater than or equal to 5 over 3. So we're going to be, again, we're going to be integrating here to find probability of a continuous random variable. X is greater than or equal to 5 over 3. Now we know that once we get past 3, the function is 0. So we're only going to have to integrate from 5 over 3 to 3 here, plugging in the constant that we found. So we're integrating 3 halves over x squared from 5 over 3 to 3. So you can factor out the 3 halves. We could skip ahead a little bit because we just integrated x to the minus 2. It was negative 1 over x. And then we do f of b minus f of a. Plugging the 3 in for x, minus -1 over 5/3. So the negative signs cancel out, and this flips over. 1 over 5/3 becomes 3/5. Common denominator of 15. So it's 5 over 15, -5 over 15 plus 9 over 15. That's 4 over 15. So that's 12 over 30, which reduces to 2/5. So the probability that x is greater than or equal to 5/3 is 2/5, or about 40%. So graphically, if we're looking at that here, this was our function. So this was 5 over 3, which is 1 2/3, or 1.666. So this is 1.2, 1.4, 1.6, 1.8. So a rough estimate here, somewhere in here, we're cutting off. And the area to the right here up to 3, that's 2/5, or about 40%. The area to the left here from 1 to this value is going to be the remaining 3/5, or 60, 0.60, or 60% probability. All right, next example here, a little bit different kind of function here using the exponential. So we're given the density for a random variable, continuous random variable x, and this represents the time in hours it takes to repair a machine. And this function, density function, is equal to 1/2 e to the minus x over 2 for x greater than or equal to 0, and it's equal to 0 for x less than 0. So the non-zero portion here, it's starting when x is greater than or equal to 0. It's 1/2 e to the minus x over 2. So it's an exponential function with an e to the minus x, so it's going to be a decreasing function here. It's the regular e to the x graph reflected over the y-axis. And so the question here is to find the probability that a repair time exceeds 2 hours. So we want this region here to the right of 2. So we're going to have to integrate from 2 to infinity. When integrate from 2 to infinity here exceeds 2 hours. Integrating from 2 to infinity, it's an improper integral. So we can express that as the limit as b goes to infinity of the integral from 2 to b. Now, when you integrate the exponential, you just get itself, right? Derivative of e to the x is e to the x. Integral of e to the x is e to the x. Now, we do have a little mini u sub here. The exponent, u is going to be -x over 2. The derivative of that is -1/2 dx. Now, normally you divide out, but the 1/2 is there. So we just have to get rid of the negative sign there, and we'll have a perfect match. Negative du is 1/2 dx, and e to the minus x over 2 will become e to the u. So the expression becomes e to the u times negative du. So again, u is -x over 2, so the exponential is e to the u. The derivative here is -1/2 dx, which is almost an exact match. We just have a negative sign off, so it's negative du. We can factor out the minus. Integral of e to the u is itself, plus a constant. Back sub in the u is -x over 2. Now we have to work with our limits, though. So we don't really need the plus c here when we have limits. So the antiderivative here, an antiderivative is negative e to the minus x over 2. We're integrating this from 2 to b, where b is going to infinity. So upper limit, we're plugging b in for x, minus the lower limit, we're plugging 2 in for x. So the question is, what happens as b goes to infinity here? So as b goes to infinity, we have e to the minus infinity, or 1 over e to the infinity over 2 is still infinity. So that term, this term here, as b goes to infinity, this expression here is going to go to 0. That term goes to 0. So this will have a finite value here, and it's equal to, the negatives cancel out, e to the minus 2 over 2 is e to the minus 1, or 1 over e. It's about 0.368. So about 37% chance that x is greater than 2. The repair time exceeds 2 hours. So graphically, we're looking at the region to the right of 2. So we're looking for that area under the curve, 2 to infinity there. That turns out to be 0.368. All right, next up, uniform distribution, continuous version. So the uniform distribution is equal probability throughout. So in the case of a continuous random variable, the function is equal to a constant on the interval AB. It's 0 elsewhere. So the graph of the density function is a horizontal segment. Now, we need the area here to be 1. We need this area to be 1. So we need the area of this rectangle to be 1. If the height is k and the width is b minus a, the difference here, the width is b minus a. So again, this distance across here is b minus a. And the height is the constant k. We need that product to be 1. So they have to be reciprocal. So k is going to be 1 over b minus a. Integral of a constant k is just kx dx, just kx. So we just get k times b minus a. So k is equal to 1 over b minus a. So continuous uniform random variable, the constant, the density is going to be 1 over b minus a. All right, so we had some formulas for the discrete case. We have something similar here for the uniform continuous case. The mean is a plus b over 2, and the variance is b minus a squared over 12. We'll do a couple examples here. So how do you calculate the mean for the continuous case? So the expected value or mean in the discrete case was the summation x times p of x. So in a very similar way here, to find the expected value or mean of a continuous random variable, you're going to integrate from minus infinity to infinity x times f of x dx, where f of x is the density. And then the variance is the expected value of x squared minus the mean squared. The expected value of x squared in the continuous case, we're integrating negative infinity to infinity x squared times f of x dx. So let's try this out on an example, a uniform distribution on 3, 7. So we know that the density is going to be equal to 1 over b minus a. So that's a quarter. And so now we're going to calculate the mean by oh, sorry, this is double checking that this does work out. When you do the integration out, you do get 100% or 1 whole. So now we do the expected value of x, which is to multiply by x there. So multiplying by x and then integrating. The 1/4 factors out, x becomes x squared over 2, and then we do f of b minus f of a, 49 over 2 minus 9 over 2, which is 40 over 2, times the quarter in front, gives us a 5, which is matching the formula, a plus b over 2, 3 plus 7 over 2, 10 over 2 is 5. So the mean here is 5. To find the variance, we have to find the expected value of x squared first. We multiply by x squared. That becomes x cubed over 3 times the constant 1/4. Plugging in the limits, 7 cubed is 343 over 3 minus 3 cubed, 27 over 3, which leads to 316 over 3, which is 316 over 12. And then we do the formula for the variance. It's the expected value of x squared minus the mean squared. So it's 316 over 12 minus e of x squared minus 5 squared, which is minus 25. 25 common denominator is 300 over 12. Subtracting, you do get 16 over 12, which is b minus a squared. It's 4 squared over 12. Or you could reduce it down to 4/3. So the mean here was 5, variance 4/3. And again, using the shortcut for variance, b minus a squared over 12, 7 minus 3, 4 squared over 12 does work out. So one thing to keep in mind, we did some introductory examples here, but we will see some situations coming up where integration by parts will be needed in this situation. When you're multiplying x times f of x, there definitely will be examples that require integration by parts. So that's something that we'll be seeing in the upcoming lessons here. All right. As always, please feel free to email if you have any questions.